Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Tencent Youtu-Lab, Youtu-LLM, Unlocking the Native Agentic Potential for Lightweight Large Language Models. Youtu-LLM is a small but highly capable language model with about 2 billion parameters. Unlike many compact models that are distilled from larger ones, this model is trained from scratch to develop its own reasoning and planning abilities. It's built specifically for agentic use cases, where the model must plan, act, and reflect over long horizons. Despite its size, Youtu-LLM matches or outperforms much larger open models, especially on tasks that require tool use, coding, and deep research, while remaining efficient enough for on-device or latency-sensitive scenarios. Modern large language models are extremely capable, but they come with heavy computational and financial costs. That makes them hard to deploy widely, especially in settings that demand low latency or run on limited hardware. At the same time, real-world agents, like coding assistants or research bots, need to reason, plan, and interact with tools in a robust way. Most small models today get there by distillation, copying the outputs of bigger models, which often doesn't give them deep, native agentic behavior. Youtu-LLM is designed to close this gap, a compact model that actually learns to be agentic during pre-training, not just during post-hoc alignment. The paper makes several concrete contributions. First, it introduces a dense multi-latent attention architecture, with a 128,000 token context window, giving the model strong long-context reasoning while staying small. Second, it designs a tokenizer that is explicitly optimized for STEM and code, improving efficiency on reasoning-heavy data. Third, it follows a multi-stage curriculum that moves from general common-sense text to STEM and then to agentic tasks over about 11 trillion tokens. Fourth, it constructs 200 billion tokens of structured agentic trajectories in math, coding, deep research, and tool use. Finally, it doesn't just report scores, it analyzes how agentic mid-training scales and how different trajectory types contribute to agent behavior. Architecturally, Youtu-LLM is a fairly standard-sized transformer for a small model. 32 layers, a hidden size of 2048, and just under 2 billion parameters. The key twist is the use of multi-latent attention instead of standard grouped attention or mixture of experts. MLA compresses the key value cache with low-rank projections and uses larger intermediate projections to increase expressiveness. This gives better attention quality at the same parameter count. The model uses a 128,000 token context window and a vocabulary of about 128,000 tokens, matching the Llama 3 family in size, but with a different token design tuned for reasoning. The tokenizer is not an afterthought here. Youtu-LLM uses a byte-level BPE tokenizer with a stricter pre-tokenization scheme. All CJK characters and punctuation are kept as separate units to avoid noisy merges, and English tokens follow a GPT-4o-like pattern. For numbers, the tokenizer only uses single-digit tokens from 0 to 9, which is important for precise arithmetic and symbolic reasoning. The vocabulary is grown in stages, starting from a cleaned base, then adding Chinese tokens, and finally adding specialized tokens for code and mathematical content. This multi-stage process yields better compression on reasoning data and, more importantly, better performance on common sense and STEM benchmarks compared to popular tokenizers like Qwen and Llama. Training is organized as a curriculum. In Stage 1, the model sees over 8 trillion tokens of mostly web and encyclopedic text to build broad common sense knowledge. In Stage 2, the mix shifts heavily towards STEM and coding, around 60% of the data, to strengthen technical reasoning. Stage 3 extends the context length from 8,000 to 32,000 and then to 128,000 tokens, while gradually lowering the learning rate. This stage consolidates long context, STEM, and coding skills. Finally, Stage 4 is the agentic mid-training phase, where about 60% of the data are structured agent trajectories. This is where the model learns to plan, act, and reflect in a way that generalizes to downstream agents. Before any agentic data is added, the authors curate a very large general corpus. They begin with more than 10 trillion raw tokens and filter down to about 8.7 trillion using a quality model trained on 600,000 human-checked examples. Web pages and encyclopedias form the backbone, but STEM and code data are deliberately upsampled. They also apply strong deduplication and decontamination, including min-hash LSH and AHO-Korasic matching, to avoid test set leakage. After upsampling the best STEM and code segments, they end up with about 10.6 trillion tokens of general pre-training data that feed the early stages of training. On top of the general corpus, Youtu-LLM is trained on 200 billion tokens of agentic trajectories. These are not just instruction response pairs. They are full process traces that include planning, actions, feedback, and reflection. The trajectories are organized into 5 main categories: structured chain of thought, mathematical reasoning, coding workflows, deep research sessions, and general tool use and planning. Crucially, these are used during pre-training, not only during post-training. The idea is to bake agentic behavior directly into the base model so that later alignment and reinforcement learning can build on a strong foundation. The first trajectory type is Agentic COT, which turns messy long chains of thought into structured reasoning traces. Instead of a single monolithic block of reasoning, each solution is decomposed into 5 tagged phases: analysis of the problem, a plan of attack, concrete actions, reflection on what happened, and a final summary. These segments are generated and refined using a stratified rewriting pipeline with large teacher models and strict filtering. The result is a 25 billion token dataset that teaches the model not just to think step by step, but to organize its thinking in an agent-like loop. For mathematics, the authors go beyond simple problem-solution pairs. They adopt an atomic thinking framework that breaks math reasoning into 11 irreducible abilities, such as symbol recognition, computation execution, formal language translation, theorem application, and self-reflection. These abilities are naturally mapped onto agent modules. Planning decides which abilities to invoke and in what order, action executes them, and feedback checks correctness. For each problem, the agent plans a sequence of atomic tasks, executes them step by step, and reflects on the outcome. This yields about 1.4 million high-quality trajectories, totaling around 20 billion tokens. In the coding domain, Youtu-LLM is trained on 70 billion tokens of trajectories that mirror real software engineering workflows. At the atomic level, the data teaches skills like exploring a repository, localizing bugs, generating patches, running tests, and interpreting environment feedback. At the trajectory level, the model sees full issue resolution sessions in environments like SWI-Gym, SWI-Smith, and SWI-Rebench, using tools such as Bash, file editors, and test runners. The authors scale tasks by generating new instances and using multiple agent scaffolds, and they scale actions by branching trajectories at critical edit and test steps. Successful paths are expanded with alternative edits and tests, while failed paths are carefully branched once to reuse data without propagating errors. Deep research is treated as a first-class agent task. For closed-ended problems, the authors build multi-hop question-answering trajectories from high-density sources like textbooks, academic papers, and professional question banks. Each QA pair is scored by an LLM judge, and trajectories are diversified using different agent frameworks and search APIs, with deliberate perturbations to make the search harder and more varied. For open-ended tasks like writing reports, they use a hybrid approach. Forward trajectories simulate the full research and writing process, including a think twice phase that forces the agent to reevaluate whether it has searched enough. Inverse trajectories start from high-quality documents, such as papers or legal decisions, and reconstruct plausible search and reasoning paths using citation graphs. Together, these pipelines yield about 60 billion tokens of deep research data. Beyond math, code, and research, the model is also trained on general tool use and planning trajectories. The authors first collect thousands of tools, from simple utilities like weather and date lookup, to complex ones like SQL and code interpreters, and organize them into a tool graph that encodes dependencies. They then perform random walks on this graph to generate valid tool execution chains. 2 LLMs play the roles of user and assistant, producing multi-turn dialogues that follow these chains, while an expert LLM summarizes and extracts planning data. All trajectories go through format checks, local execution tests where possible, and LLM-based quality scoring. A small fraction is deliberately corrupted by deleting tools or shifting topics to create negative examples that teach the model to recognize and recover from bad plans. After pre-training, Youtu-LLM is turned into an assistant through supervised fine-tuning. The SFT data covers a wide range of tasks: mathematics, coding, scientific reasoning, agent workflows, general knowledge QA, instruction following, role play, creative writing, multi-turn dialogue, and safety. For many prompts, the authors add explicit long chains of thought. When no reference answer exists, they ask strong teacher models to generate both reasoning and answer. When an answer exists, they either reconstruct a consistent reasoning path or discard and regenerate low-quality responses. The resulting dataset is cleaned in several passes. Simple heuristics remove truncations, garbled text, and repetition loops. Teacher models score coherence, fluency, and factual accuracy. and 32-gram matching removes any overlap with evaluation benchmarks. The supervised fine-tuning itself is staged. In Stage 1, the model is trained almost exclusively on logic-dense data, mathematics, programming, scientific reasoning, and agentic tasks. This phase is meant to cold start the model's reasoning engine, teaching it to build structured arguments and multi-step solutions. In Stage 2, the training expands to the full diversity of tasks, but still includes the Stage 1 subsets to avoid forgetting. Here, the authors also introduce a dual-mode behavior. Some examples keep their full chain of thought, while others have the reasoning stripped, and special control tokens indicate whether the model should think out loud or answer directly. This allows developers to toggle between a transparent reasoning mode and a faster, concise mode using the same model. On top of SFT, the authors apply reinforcement learning to sharpen reasoning and align behavior. For math, they use competition-style problems with structured answer formats that can be automatically checked. For code, they rely on execution-based rewards and input-output prediction tasks. Complex instructions and safety scenarios are scored with a mix of rules, reference answers, and LLM as a judge rubrics. To keep training stable, they enforce global constraints. Outputs must preserve required thinking tags, stay in the target language, and avoid pathology repetition. They also show that using FP16 instead of BF16, combined with a consistent sampling scheme that filters out prompts with large train rollout divergence, significantly improves training inference consistency and leads to better math and coding performance. When evaluated as a base model without instruction tuning, Youtu-LLM performs very well. It consistently beats other small models like Qwen 3 1.7b and small LM 3.3b across common sense, STEM, and coding benchmarks. On tasks like GSM-8K, MGSM-ZH, and math, it reaches or approaches the performance of the larger Qwen 3 4b base model. In coding, it does especially well on human eval, MDPP, and crux eval, and it handles long context tasks with high recall on needle-in-a-haystack tests. Overall, the base model is not just a language model, it's already a capable technical reasoner. After instruction tuning and reinforcement learning, the Youtu-LLM 2B instruct model becomes even more impressive. It outperforms similarly sized models like Qwen 3 1.7b and small LM 3.3b across common sense, instruction following, STEM, and coding benchmarks. In many cases, it even matches or exceeds the performance of the much larger DeepSeek R1 Distill Llama 8b model, especially on coding tasks like human eval and MBPP, and on text reasoning benchmarks like DROP. On challenging STEM benchmarks such as Math 500, AIM, and GPQA Diamond, it remains highly competitive, showing that a carefully trained 2B model can punch far above its weight. To measure agentic potential before building full agents, the authors use APT Bench. This benchmark probes whether a base model can plan steps, choose actions, and handle atomic subtasks in 4 domains: coding, deep research, math, and general tool use. The tasks include multiple choice planning questions, text completions for actions like bash commands, and fine-grained checks of feedback and citation correctness. On APT Bench, Youtu-LLM 2B scores close to the larger Qwen 3 4b base model across all domains, and clearly surpasses other small models. This is strong evidence that the agentic pre-training has successfully endowed the base model with robust agent-like skills. The authors also evaluate full agents built on top of Youtu-LLM 2B. For deep research, they use Gaia and Xbench, with a React-style framework and LLM as a judge scoring. For coding, they test on SWE Bench Verified and Enconda Bench, using standard scaffolds like R2eGym and OpenHands. For tool use, they rely on BFCL v3 and Tau2 Bench. Across these benchmarks, Youtu-LLM 2B consistently outperforms other small instruct models and often comes close to or surpasses larger baselines. The gains are particularly notable on Gaia and SWE Bench Verified, where the model's planning and error correction priors, learned during the agentic mid-training, translate directly into higher resolve rates. A key question is how much agentic mid-training actually helps. The authors track APT Bench scores as they increase the amount of agentic trajectory data from about 34 billion to 340 billion tokens. The curve follows a clear logarithmic trend. The first chunk of agentic data yields a big jump in performance, and further data continues to add value, though with diminishing returns. Overall, the average APT Bench score improves by more than 6 percentage points. When they compare post-trained models with and without agentic mid-training on real agent benchmarks like Gaia and SWE Bench Verified, they see relative gains of around 14% on average, confirming that the mid-training benefits survive through SFT and RL. The paper includes detailed ablation studies to understand what each trajectory type contributes. Agentic CoT data significantly improves planning and math tasks, teaching the model to structure its approach before computing. Math trajectories, especially when masked to focus on assistant outputs, enhance both planning and feedback, with performance improving as more data is added up to a saturation point. Deep research trajectories, when properly masked to ignore noisy tool outputs, yield strong gains in both planning and action on DR tasks. Code trajectories dramatically improve environment setup and issue fixing, and even allow the 2B model to surpass a 4B baseline on some issue fix subtasks. Tool use trajectories are most helpful at moderate sampling rates. Oversampling them can actually degrade code and tool performance, highlighting the need for balance in the data mix. To make the behavior concrete, the authors present several case studies. In a math example, the model recognizes that the key is to find a smaller ring containing the square root of 3, and it deliberately adopts a counterexample strategy instead of blindly manipulating formulas. In a deep research example, the agent retrieves official census data, then gracefully recovers from a failed tool call by doing the arithmetic internally rather than looping or hallucinating. In a coding example from SWE Bench Verified, the agent navigates the Sphinx codebase, identifies that a string is being concatenated with a type var, and implements a minimal, type-safe fix while preserving existing behavior. Across these cases, you can see the full agentic loop: analysis, planning, action, and reflection, mirroring the structure of the training trajectories. Despite its strong performance, Youtu-LLM is not a silver bullet. It still lags behind the largest proprietary models on the most demanding agentic tasks. Long chains of thought and lengthy trajectories also increase inference latency and compute cost, which can be a concern in real deployments. The current model is text-only, so it cannot yet reason over images, audio, or other modalities. The authors outline several future directions, moving toward world model-style training that better simulates environment dynamics, exploring more efficient architectures like diffusion-based LLMs to speed up inference, and extending the framework to multimodal agents that can perceive and act across richer environments. Stepping back, Youtu-LLM shows that you don't need tens of billions of parameters to get strong agentic behavior. With a well-designed architecture, a reasoning-aware tokenizer, a staged common-sense STEM agent curriculum, and 200 billion tokens of carefully structured trajectories, a 2 billion parameter model can plan, act, and reflect at a level that rivals or surpasses much larger open models. The work also demonstrates that agentic mid-training is a powerful lever. Injecting agent signals during pre-training pays off later in both base and instruct models. This pushes the frontier for small deployable LLMs and brings us closer to practical on-device agents that can truly understand tasks, use tools, and solve complex problems end-to-end.